Hello and welcome to our third coffee break cold brew edition of the summer. Today we rebroadcast two very cool sessions related to crack inspection. First, Sergio Grand will talk about lift-off management and far side inspection. Then, Fred Reverdy will discuss crack characterization for TFM using indirect modes. As usual, if you have any questions or comments after watching the video, contact us at info@edify.com. Thank you.
For the lift-off management, we usually look at the impedance plane, but the impedance plane itself can always be different. So the operating point can vary depending on which material we're working with. So, for example, here with aluminium, the operating point is at a certain point on the curve, and then if you move the probe, let's say you balanced on aluminium, then you move the probe in air, you get a certain lift-off signal here illustrated in red dashed lines. And let's say on carbon steel, you will be somewhere else on the impedance plane. So your operating point is somewhere different. Hence, the lift-off signal will look differently as well compared to your defect signals. So this is always to respect when you need to know on which material you're working on, and you preferably balance on this material and then make a lift-off, and then you see the operating point changing. And when you have all this information, the best way to improve the signals is if you take this view. So we switched from the aluminium lift-off point, and we only take this portion of the impedance plane, and we balanced on aluminium. So where you see the 0, 0 was directly on the material. And then we rotate the whole signal in the Magnify software so that the lift-off will be horizontal. So when the lift-off is horizontal, then we will only look at the vertical change in the signal. So as you see now, if we have a lift-off change, the signal would move from operation point a bit towards the left, but the defects will always go kind of vertical. So by only looking at the vertical change, we kind of cancel this lift-off change, because that's not what we want to be sensitive to. So we choose to rotate the signal in this direction, and then we won't see the lift-off affecting the signals that much when we have a good phase separation. And afterwards, to improve this signal that we captured, we apply some horizontal gain only in the y-axis. So it won't, you see the difference, the lift-off gets boosted a little bit, but the defects get boosted much more. So you will see the defects even clearer. So that's the main principle how we manage lift-off. There are other ways, but this is more hardware kind of. We can choose different coil sizes. So here's illustrated on the top right side. There is the black coil is a 2 millimeter coil. The green one is 3.5, and the orange one is 5 millimeter. It's just an illustration, so don't take all the values here for granite and set in stone, but just to give you an idea. And in the graph, you see the normalized defect signal. So 1 is 100% of the signal. So the coil is touching, the probe is touching directly the material. And below, you see the lift-off amount. So for this 2 millimeter coil, the black coil, and we lift this one up in the air. So we perform a lift-off. You see, let's say after 1.5 millimeter of lift-off, we already lose almost all of our signal. But on the other hand, if we take a bigger coil, 3.5 or even a 5 millimeter coil, they can tolerate a bigger amount of liftoff. So the signal is obviously maximized when you are directly in contact with the surface, but this cannot always be the case. Maybe if you have a paint layer, or there's just a certain, maybe a rubber layer of a certain thickness. So if this is like 1 to 2 millimeters, then if you know this thickness, then you can choose, or we can choose the coil size accordingly that we put inside the probes. So meaning now for the 2 millimeter coil size, after only 1 millimeter of liftoff, we're already down to like 25% of the maximum signal strength that we could have if we were directly in contact with the material. On the other side, for the green coil, 3.5 millimeter, after 1 millimeter of liftoff, we still have over half of our signal strength. So if this we can also play, it depends on what type of defects we're looking for. And then also that the bigger we go in the coil size, the more liftoff we can tolerate. But we will be a bit less sensitive to really, really small indications. So there's always this sweet spot we have to find between taking super small coils, super big coils, and then being sensitive to what we want to, and maybe liftoff or not liftoff. I hope this gives an idea on how we choose the elements inside the coils, inside the probes. But in general, what happens when you have liftoff? Here's an example of the 3 cracks. One is 0.5, 1 millimeter, and 2 millimeter. They're directly on the operating point where we balanced, and we add liftoff. That's at 0 millimeter liftoff. Then we add some liftoff, and you see that all the defects get kind of smaller and travel towards the left, towards the more liftoff. So they will move along this liftoff curve. They will stay horizontal, but afterwards they will move wherever the liftoff curve is going, because they have a certain amount of liftoff and the signal goes in this direction until the defects become smaller and smaller, and we won't see them anymore, and we're just in air. So this is what happens usually, that the phase stays the same of the defects when only the liftoff changes. They will just be seen as a smaller amplitude. So all this information will be important to what I show you afterwards. So yeah, that's how we handle liftoff. It was a short recap of what we do with liftoff. Now we'll go over to far side inspection. And here is a small illustration. That's a probe that will move along a surface with a direct contact. It's always preferred to have a direct contact with the inspection surface. And a probe that looks for far side indications, it's usually used with a low frequency. So something between 100 hertz and 25 kilohertz. And also, we should have a material that is non-ferrous. Let's say if it's a ferrous material, then the eddy currents will kind of be pushed to the surface and won't be able to penetrate the material, as for stainless steel or aluminium. Again, we will look at the impedance plane to see our signals. And when you move the probe over those defects, you see the first defect is bigger in volume, is deeper, closer to the surface. So we see it with a higher amplitude. And then the smaller the defects get, or the further away the defects are from the surface, they become smaller, and then they open up with the phase. So they move towards the right side in this case. So that's how we can also differentiate how deep a defect is by looking at the phase of the defect. Yeah, that's it. Deeper defects increase phase shift. For the far side inspection, we have a rule of thumb that we often, the first time you hear about an application, we ask, okay, how thick is the material? What material do you have to inspect, and how deep and how big are your defects or your indications? And if this rule of thumb, here's the coil illustrated, the coil OD. It's more or less the OD of the coil can be translated to the depth of penetration. That's a rule of thumb. It can vary, but it gives you a good idea of if I have a 5 millimeter coil, my depth of penetration will be roughly 5 millimeter, where I still have a good quality signal. In some cases, it can be more, but then we would need to tweak the setup accordingly, and it also depends on which material you're working with, surface condition, and several things. So just maybe keep this in mind. And if you want to penetrate 5 millimeter deep, you take a 5 millimeter OD coil in the probe coils. And you will be sensitive to indications that penetrate at least 20% of this wall thickness from the far side, and that are maybe twice the volume of the coil, or twice the diameter. So you see it here illustrated. The red part is the flaw, the defect, and it's roughly twice as long and 20% depth of penetration. Okay. Now, if you put those two this information together in one impedance plane, so you'll see we perform a liftoff usually. Then here's the liftoff is already rotated horizontally, and then we maybe scan over a small notch that is surface breaking. Then it will be a shallow or a small amplitude with a smaller phase closer to the liftoff. If we scan a bigger notch, so the illustration goes a bit too far here, it should only scan this one, we will have a nice defect shape. It could look like this. Then, yeah, large amplitude, greater phase shift towards the liftoff. And then that's the third indication that is a little bit subsurface, but still closer to the surface. But you see it will open up a bit and also be a bit smaller because it's not surface breaking. And then the last, if a larger phase shift, then the last indication, well, scan this one, should still be on the material, has a even greater phase shift, but it's quite small now because it's deep inside the material. So yeah, the deeper it goes, at one point we will also lose it. So we should stay close to the surface. With a certain amount of liftoff, we will start to see less and less of the indications, but they stay with the same phase. And the further they are in the material, the further they will open up in the phase. And at one point they will also, let's say, disappear because they get too far away for the eddy currents to see them. Now I will come to the scan. I have my plate here with several flat bottom holes. Some are all the way through. There are 3 all the way through. And basically there are 4 types of holes of 4 depth. The most shallow one is 0.79, 0.8 millimeter. This one 1.6, around 3.17, and 4.776. And the plate thickness is 6.4. So some are all the way through as well. I will not focus on those because they will be easy to see. And this one is like 75%, 50%, and 25%. And I will be using an iFlex, one of our standard iFlex probes, the extra large one, because you want to penetrate to roughly 6 millimeters. So I will have 6 millimeter coils, and I'll be working in a long single driver topology for the people who know what topologies are. And I will go quite low in frequency. So the central frequency of this probe is 5 kilohertz. But in my setup, I will go down to around 1 or 0.8 kilohertz. So let me switch to 95. We took some test scans before. let me just show you what I have here. That's the iFlex probe with rather big coils. And I plugged a standard encoder to it. And then I want to make sure, well, now I know that, let's say, my defects are here and there is a long notch. So I want to balance around here where I don't have any indications. So I have to have a nice balance point. So if you know this in your application, it's preferably to balance on this surface. So let me balance. And then I'll just scan along here. I did the lift-off adjustments already in advance. So, and that's a good example for something you should not do. I moved a bit too fast, so that's why you see two black lines in the scan. Yeah, because we're quite low in frequency, I should move a bit slower. Those holes are all the way through, so I want to focus on this section here. And what I did as well in advance, I added the sizing curve. And my sizing curve sizes with the phase of the indication. So here, for example, for this indication, we have a 91.4 degrees. And because I calibrated the core, I built a sizing curve accordingly. It sizes me this indication as 3.1 millimeter. And if I maybe switch back real quick just to show you, 3.17. So the sizing is not perfect, but I guess it's quite accurate. And just please don't forget, if with pancake eddy currents or with an iFlex probe, we do it's more an approximation. We cannot call it sizing because it always depends on how many points we have on our sizing curve. And so if you just have like 2 example points, then the curve would just be one straight line. It might be not super accurate all the time. So it's more an estimation. And then also maybe one scan to another can vary a bit, and then also where you place your cursor. So now it gives me something between, down here you see the value, 3.2 millimeters to 3.1. If I take this one, it's around 1.8, 1.7. So just to switch back, it should be around 1.6. So I guess we're not off too bad. This one, make the cursor a bit smaller. I think it has the same. Yeah, 1.7. You're also around 3.2. So here I didn't have any lift up. So now we'll add a sheet of, let's say, 1 millimeter. And I'll perform the same scan, and just keep in mind how the scan looked like, how well you see the indications, because now the indications should become a little smaller because we're a little bit further away from the surface. So balance, I scan, I try to move a little bit slower now. Don't have a black line. All right. I was not perfectly in the middle. So let's focus on those. And that's 2 other indications we saw already. But let's refocus on those. They were clean. So, okay, I didn't focus on the voltage value we had, but I think we have something like we had before 1.2 maybe. Now we are down at like 0.8, so we lost some amplitude of the indication, but the phase is still very similar. So we're around 91 degrees, and we're still, since the sizing curve is based on the amplitude, we still get the similar sizing of 3.2, 3.3, 3.1. If we take this one, 4.7, and I think we should be, around 4.76. And here we also lost some amplitude, but it didn't affect our sizing. So that's really helpful in Magnify, that you can build your sizing curve based on the phase of the indication. I think I saved the other data. So let's just say here we're around 0.8 volt. And if I go to the sizing that took before, what's this one? No, I don't want to save it. Yeah, here I took an example scan where I moved super fast. I wanted to see where the limit is. Take this. And yeah, we were around at 1.5 volt, and yeah, this one was a bit shallower. So yeah, I hope that gives you a good idea of how sizing curves can be performed in Magnify, and how we tolerate, or how much liftoff we can tolerate, and how we manage liftoff, and also that for Farsight, even though they're only like 25% deep, we can still see them. Oh, I didn't show you this one. Sizes me 0.8 millimeter, and it's actually 0.79. So that's not too bad. And yeah, there's a certain amount of liftoff, we will lose the defect, and you won't be able to size it anymore. But we can tolerate up to a few millimeters of liftoff, and still penetrate like 75% of the material.
Okay, so when it comes to TFM, according to ASME, it is possible to image defect through a multiplicity of modes. What is a mode? A mode is a different ultrasonic path. So it can be a direct path like LL, LT. It can be a corner path, which is what we're going to talk about today. It can be an indirect path, which is the one like LLLL, so CAL, 40. So essentially 4 layers. So we are most familiar with direct modes. Direct modes are pretty straightforward. We start from any transmitter, so any element that fires. We propagate through the component with either L or T, go to a pixel of the region of interest of the TFM, and back to all the receivers using, again, L or T wave type. So we have 3 possible modes, LL, TT, and LT or TL, which is essentially the same mode, but we rarely see this one. The main applications for the direct modes can be HTHA, so high temperature hydrogen attack. We have an image right here. We have like really small cracking, like 20 to 50 micron. We can use it for corrosion mapping, and we can also use those modes for weld inspection. So here is a multi-group TFM inspection using the new capture 3.2. All right, so we also have the indirect modes. So the indirect modes involves 2 reflection of the back wall. So we propagate through the component, have a first reflection of the back wall, go to the pixel, back to the back wall, and back to all the receivers. So you have 4 letters. Typically we use the 4N or the 4T, but you have to know that you have typically up to 16 indirect modes. So we rarely use 16 indirect modes. Typical application is looking at bevel after reflection on the second leg. So like a typical here, it's a crack along the bevel. But today we're going to talk about corner modes, also called self-tandem by others. So these corner modes involve, again, propagating through the sample, 1 reflection of the back wall to the pixel, and directly back to all the receivers. So you have 8 possible corner modes. I'm listing all of them here, but we rarely use all of them. And I would say mostly right now we are limited to like 3T or things like that due to like comprehension of those modes. What are the typical applications? It's detection of planar defects, such as lack of salvable fusion or cracks. We are really looking at, those ones are really looking at specular echo perpendicular to this planar defect. So those are typical images you can obtain with corner modes, like a 3T here for a notch along the back wall, a TLL for a notch in the midsection of the weld, or a TTL for like these types of inclination. And what we like about those modes is they tend to draw, between quotes, the defect. It's very similar to like a lack of salvable fusion on the second leg. When you use PUT on the second leg, you have your perpendicular to the bevel, and you have this nice specular echo. So this is typically what these corner modes do. So actually, looking at an elliptical defect right here, we move the probes this way. So you have the TFM here. And when you look at the front view, you actually draw nicely the shape of the elliptical defect. If you drop this into the 3D view and superimpose that to the defect, you really see that we're able to image the defect perfectly. So there is some potential to those defects in terms of imaging. But there are things to check, to make sure we do properly. So typically, a corner mode is very similar to a pitch catch mode with TFM, with PAUT, using the same probe. We have a direct pass right here, a reflected pass right here. So where we go T and T, then we combine to a direct T this way. So at the end, what you obtain is this highly focused point, because we are using TFM, so we are focusing everywhere within the region of interest. So this is the path that this 3T mode is taking to reach that pixel. And for that particular configuration, we have a focal point of about 2.7 millimeter by 2.3. So this configuration is using a 5 meg probe, 64 element, shear wave, obviously, and pitch of 0.6 millimeter. So the focal beam is a little bit bigger than if you purely use a TT mode, because you are looking at kind of the intersection of the reflection and the other one. So this tends to elongate a little bit the focal point. The 3T tends to have a preferential direction, which is the bisectrix between the direction after reflection, like this one, and the receiving angle. So for this particular pixel, the direction of the energy is pretty much horizontal. It's kind of going this way. So meaning that we are going to be sensitive to defects perpendicular to that direction. So this is important because the corner mode are kind of looking for specular echoes. So let's look at how this direction evolves as we move our focal point along a vertical line, kind of following a vertical defect. So here we are starting here. We see that the direction is going this way. Now we are pretty much horizontal, so sensitive to vertical defect, starting to go up a little bit and higher and higher. So the higher the focal point, the higher the direction of the energy as well. So the less sensitive we are to vertical defect. Also, we see that we have less energy, less field energy on the top compared to the bottom. So if we were looking at a vertical defect, we will tend to be more sensitive right here, where the direction of the energy is horizontal, as opposed to here. So that's why there was a tool that was developed. There's many names: sensitivity map, others call it acoustic influence map, or AIM. So it was first developed by my colleague, Combo C in her PhD. So you have here a link to one of her publications. So she's still with us at M2M. And the idea of this sensitivity map is to kind of draw within the region of interest of the TFM the sensitivity of one mode, so here the 3T, to one defect orientation. So here we are only looking at purely vertical defect all across the region of interest. And we see that for this configuration, the one we have selected with the probe in the region of interest, we will be very sensitive right here. Like if we have a vertical defect right here, we'll have a pretty good signal-to-noise ratio. But if the defect was up here, that one would not be sensitive to it. Why? Because if we go back to this, because the direction of energy is going this way, and we are looking at vertical defect, so we wouldn't have any specular echo. this is only one direction of defect. So this is very important to remember. So what happens when we have vertical defects? What can we expect in terms of sizing? So let's say we have an 8 millimeter notch. We are still within the red region of our sensitivity map. We look at the 3T mode. So like we draw nicely using the envelope. It's perfect. And if we look at an echo dynamic, so we look at the energy along the z-axis, we can see that for this 8 millimeter, we have about 5 dB drop. It's actually 5.2. So it's not very far to our typical 6 dB drop. So we could potentially use our 6 dB drop as long as the defect is within this highly sensitive region of the region of interest. But what happens if our defect is a little bit taller? So let's look now at a 15 millimeter defect. So the defect now is reaching into kind of the green region. We look at the TTT TFM image, and we see that we are still drawing our defect. But when we look at the echo dynamic for the 15 millimeter, there is actually a 9 dB drop. So we cannot really use a 6 dB drop anymore, because if we were to use a 6 dB drop here, we would undersize our defect. We will actually measure about 13 millimeters. We'll make 10 to 15% error on measurement, just because the defect is not in this region anymore of the sensitivity map. So when it comes to sizing using corner mode, it can be an issue, and you have to really make sure that your defect, knowing the orientation, is within the part of the sensitivity map where there is very small variation in amplitude. So I said before that this sensitivity map, or AIM, is calculated for one direction. So this is what we have for 0 degree defect. So here, looking at the vertical defect, let's see how this sensitivity map evolved as we are changing and tilting the defect. So I'm going to do it by a step of 2 degrees. So the same map, but for defect with a 2 degree fall. And we can see that the sensitivity map is going down, meaning that our TFM, our 3T mode, wouldn't be sensitive to any defect right here. It will be very sensitive to the bottom of the TFM image. So if we have this 15 millimeter defect, or even here 8 millimeter defect, we wouldn't be sensitive at all. And to illustrate that, I mean, in real life, it's hard to predict the orientation of defects. Unfortunately, they are not like these nice notches that we like. If you look at weld prep, according to welding standard, do you have a tolerance of plus minus 2.5 degrees? So you already have a 5 degree gap on the bevel itself. So let's look at 8 millimeter notch right here, and let's look at a reconstruction of a 3T mode for the defect evolving from 0 to 10 degree. And here we're going to do the TT mode, so the direct mode, but we're going to display the first leg and the second leg. So essentially here we are doing the TT, and here the 4T on the same image. And for the, at 0 degree, we can see this nice corner echo and the tip diffraction here on the first leg, tip diffraction on the second leg. And this is what we are going to look at, how this changes with defect orientation. And here we have our 3T mode for the 8 millimeter defect, the same image we had before. So let's see how it changes. Now we have 2 degree, barely any changes. 4 degree, we can see that we are losing amplitude right here. 6, losing a lot of amplitude right here. 8, and 10 degrees. So you see how the 3T mode was okay at the beginning and then starting to lose amplitude. If we look at the TT, at 10 degrees, we still have our corner echo right here with the defect. We can see that our tip diffraction on the first leg is located perfectly with the defect. On the second leg, it's shifted a little bit. But going back to even 4 degree, we can see here that there is a drop in amplitude on the higher part of the defect. And if you remember the sensitivity map, it's because as the angle of the defect goes up, the sensitivity map was kind of going down, being less sensitive to this part. While the TT mode is still okay to measure the defect. Of course, you have to make sure that your tip diffraction has enough sensitivity itself, 12 dB or more, but we'll see examples before what this is typically not a problem. All right, so let's look at sizing of what I just did with the TT mode based on tip diffraction and corner echo, and a minus 6 dB drop for 3T. For 0 and 2 degree orientation, And this is good. We measure the height of the defect perfectly. The TFM pixel size is 100 micron, so this is within the tolerance of the precision of the TFM. But starting already at 4 degrees, the TT mode is okay, but the 3T mode is starting to undersize it, and then after it quickly undersizes it down to 1 millimeter, which will actually be the size of the focal point at the bottom of the screen, of the TFM. While the TT mode is sizing perfectly, 7.9 is still okay because we are not looking at this distance, we are looking at this distance. So for 10-degree defect, that distance is 7.9 millimeter. So we see that a slight misorientation, I mean 4 degrees is not a lot, we can lead to a huge undersizing using the corner mode. So when it comes to real defects, again, they are not this smooth, nice defect. They tend to have multifacets when they propagate. And we have a weld here. It's a 1-inch weld with a defect that starts initiate here, close to the root, and start to propagate this way, kind of vertically, and then follows the bell. And so we have here the TT mode with the first leg and second leg. So again, this is the TT and this is the 4T at the same time compared to the 3T. So let's switch to capture. So here I have my TT, 3T. So if we wanted to size this using the TT mode, so I'm going to go here. And I kind of see, I'm going to zoom a little bit. Kind of see that I have a tip diffraction right here that I see here. I'm going to increase the gain. And I can actually see that I have a signal to noise ratio of about 20 dB. So I have pretty good signal to noise ratio here. So to size it, I will essentially position it on the maximum of the tip diffraction here. And I will do the same on the corner echo. So I'm just going to go roughly. It's kind of roughly here. I will need to do it more accurately, obviously. And my delta depth here is about 6.5 millimeter. So here, the height of my defect will be about 6.5 millimeter. Now let's look at the TTT mode. And here, I'm displaying the echo dynamic along Z. So I'm projecting all the maxima along the Z-axis. So here I have my maximum right here. You can see this is right here. I'm going to zoom. I'm going to position my blue cursor to have 6 dB. So I have 6 dB between my data cursor and my measurement cursor. And I'm going to put one right here. My blue cursor is at 0. So I can see that the height of my defect is 1 millimeter, which I know is not the case because I just measured it to be 6.5 millimeter. The problem here is my 3T mode, due to the face of my defect, is not representing the defect nicely. It's not drawing my defect nicely. And even if I was to kind of use that as kind of the top of the defect, we see that we are still not measuring the height of the defect properly. So really, we have to be careful when using this mode for sizing purposes. The amplitude right here of this echo is about the same as the amplitude of the corner echo. All right. One other aspect to pay attention to when using corner modes is thickness. Because they rely on a backward reflection, they are very sensitive to the thickness input you input in your algorithm, so in your system. So to illustrate that, I'm looking at a 3 millimeter notch image using a 49 millimeter thickness. So the original thickness is 50 millimeter, but I'm telling the system I only have 49 millimeter. So I'm making a 2% error on my thickness measurement. So here, this is my TT with my 4T again, and this is my 3T. So I'm telling my system my back wall is here, but actually the real position is this one, kind of the center of the corner echo. So I'm making this 1 millimeter error. So if I want to size it using TT, I will look at the maximum of my corner echo, maximum of my tip diffraction, and I will measure the height of my defect, and I find my 3 millimeter. Here I'm telling my system I'm at 49 millimeter, the real thickness is 50. when we use corner modes, we don't calculate anything outside of the component because they assume a reflection of the backwall, so there is no reason in calculating pixel outside. So if I now use a 6 dB drop, I'm only sizing at 2 millimeter. So essentially, I'm making an error which is the same as the error I'm making on my thickness measurement. So you see that it is, when you do corner mode, it is very important to input the perfect thickness of your component. Kind of to illustrate all of what I've said before, we're going to look at the 5T mode. So the 5T mode, I think I would classify it as a corner mode as well. It is very similar to the 3T mode, except that it involves an extra reflection. So we have one reflection of the backwall, one reflection of the surface, back to the defect, back to the backwall, and back to the probe. So it is the 5T, in the same way as the 3T, is effective for vertical defects, but located on the same side as the transducer. So we are kind of going to look at the same influential parameters as 3T. So essentially, defect orientation, thickness measurement, using like a 3 millimeter notch this way. Actually, this notch. So I kind of adjusted my index offsets to make sure that I have a good sensitivity map, not sensitivity map. I can see here that for that particular position, I have, for the defect right here, I have very small variation of sensitivity. Again, remember, this is for only 0 degree defect. The map I'm drawing right here is only for 0 degree defect. Anyhow, it seems that I have good coverage of my area looking for vertical defect. For the TT mode, this is what I'm calculating. It's kind of overkilling right here, but I'm using this entire TFM box right here, which in a sense would be a TT, a 4T, and a 6T. So I'm looking at my defect right here, kind of on the second leg. So this is the result I have for my 3 millimeter notch. I'm going to do a zoom. So I'm making a zoom of this area right here. So I have my corner echo. I have my tip diffraction on the second leg. This is my tip diffraction on my third leg. And this is my typical 5T mode reconstructed after a rebound. So sizing is kind of exactly the same. I will be using tip diffraction to corner echo for my TT, and I will extract my 3 millimeter. Here I'm going to use a 6 dB drop, and I will size it at 3.2 millimeter, which is pretty much the same as 3 millimeter. My pixel size is 100 microns, so I will say I'm close to be within my tolerance of my grid. So now, again, let's look at what happened when we start tilting the defect from 0 to 10 degrees. And here I'm only using a 3 millimeter defect. So I'm not using a very high defect again. I'm trying to use a small defect. And kind of the same is happening right now. We see that the TT mode, I have my corner echo, I have my tip diffraction here positioned correctly. Again, my tip on the third leg is not necessarily positioned correctly, but I don't really care. I will be using this one and this one. And we see here that on the TT mode, I have completely full separation. Don't draw my defect anymore. And even this kind of diffraction is not located in the right location. So if I go back here, I use a 3 millimeter notch on purpose. I really wanted to stay within this contained region here of my sensitivity map. I didn't want to have a long defect. I just wanted to see the influence of orientation for a defect that's really, really close to the top surface. So we see that kind of the same way as the 3T. Quickly, even at 4 degrees, we lose amplitude here, and we are not sizing our defect properly. So the error is kind of the same as the 3T before. I'm not going to put it here. But OK. So now let's look at the sensitivity of the 5T on thickness measurement. And I'm going to use the same mistake I made before. Instead of 50, I'm going to put 49 millimeter. But now I have one reflection of the back wall, one reflection of the top surface. So I'm going to make the mistake twice. So instead of making a mistake of 1 millimeter, I'm going to make a mistake of 2 millimeters. Again, on the TT mode, I have my corner echo and I have my tip diffraction. If I measure the distance, I still have my 3 millimeters. So I'm not really sensitive to my variation of thickness. What's happening here on the 5T is interesting. It's a little bit different compared to the 3T. Actually, like this 2 millimeter error, so which would be a kind of 4% of the travel path, my defect is supposed to be here. And now it's kind of positioned after. It's not even positioned at the right location, which is okay. It's not a big deal. I'm not positioning the defects at the right index position. But if I do my -6 dB drop, so I have my echo dynamic here, 6 dB, here I would be oversizing my defect if I'm only using this and if I'm not using that information. So we see here that the 5T is even more sensitive to errors we are making on the thickness measurement. All right. So I'm gonna conclude. We are making shorter coffee breaks. So TFM offers the advantage of seeing defect through different modes. We have the direct mode, we have the indirect mode, we have the corner modes. There is potential here. And some tools such as sensitivity map have been developed to help operators see a sensitivity of some modes within the component thickness. But I really want to put some stress here, but on that, you really have to know the limits of those modes. They are highly sensitive to defect orientation and to component thickness. So before using them, you really have to know your components and kind of like the preferential direction of your defect. Otherwise, it's going to lead quickly to undersizing, and undersizing is not permitted per code.